Okay, the first one is y equals the angle whose sine is 1/2. Now, when I'm looking at the sine graph, I need a positive and a negative quadrant for it. So I'm getting the first quadrant and I'm getting the fourth quadrant. That's the interval to which I'm restricting my attention for the inverse of sine. You should know by now what angle has as its sine 1/2. 30, and since it's positive, it's the first quadrant, and in radian measure, that's pi over 6. Let's take the second part of this problem. This is read the cosine of the angle, the angle whose cosine is negative square root of 2 over 2. For cosine, we're restricting our attention to the first and second quadrant. One positive, one negative here. What angle has as its cosine positive square root of 2 over 2? 45. So that would be the first quadrant. But we're not in the first quadrant because it's negative. We're in the second quadrant. And 45 is also pi over 4. So what would be the angle that would come around from initial to terminal that would have a reference angle of pi over 4? 3 pi over 4. Now we don't know an angle whose tangent is 1/4. It's not 30, 60, or 45, but I can make a triangle. There's the angle that has a tangent of 1/4. I don't know it. I don't care to know it in degrees or radians. But I do know that tangent is opposite over adjacent. And with the Pythagorean theorem, 1 squared plus 4 squared equals the hypotenuse squared. I have that the hypotenuse is equal to the square root of 17. And now I need the cosine of angle x. And the cosine is adjacent over hypotenuse. So the cosine of this angle is equal to 4 over the square root of 17, but I need to rationalize because I never leave a radical in the denominator of a fraction. So I get 4 square root of 17 over 17. So again, it's not 30, 60, or 45, but I can make a right triangle of which the cosine is adjacent over the hypotenuse. So I have 2 squared plus, I'm going to call this y, plus y squared equals 3 squared. 4 plus y squared equals 9. Y squared equals 5. So y is equal to the square root of 5. Sine of angle x now is opposite over hypotenuse. But I'm not going to change tangent. I'm just going to leave it, tan x. So I only made a substitution of secant x equals 1 over cosine x. And I'm not going to do anything to the right-hand side. Now, if I multiply cosine times 1 over cosine, what do I get? 1. And if I have 1 over the tangent, that's the cotangent. All right, now I could replace the right-hand side with tangent because sine over cosine is tangent, but I'm not going to. I don't need to, so I'm not going to. On the left-hand side, I'm going to make again a substitution for secant of 1 over cosine. Now, this is good practice of a complex fraction, a fraction within a fraction, because it helps to review that concept. How do I get rid of a fraction within a fraction on the left-hand side? Multiply all 3 quantities, the 2 in the numerator, the 1 in the denominator, by all the denominators that you have, and you have just one denominator, which is cosine. It's cosine times the numerator and denominator. Don't forget to show me that you're multiplying numerator and denominator by the cosine. Cosine times 1 over cosine is 1. And cosine times cosine is cosine squared. And in the denominator, I have cosine x times sine x. And again, I don't prefer to make a substitution on the right-hand side. Now, I'm using a Pythagorean identity here. Okay, I'm going to show that here. I don't know where. All right, so sine squared plus cosine squared equals 1. That's a Pythagorean identity. And if I want to take cosine squared, I can write it as 1 minus sine squared. If I want to take sine squared, I can write it as 1 minus cosine squared. So I'm going to take sine squared equals 1 minus cosine squared. I could have taken cosine squared equals 1 minus sine squared, but I'm using that Pythagorean identity as a substitution. So now in place of 1 minus cosine squared in the numerator, I have sine squared. And I'm keeping the denominator the same. Now I see multiplication in the denominator. I can divide out sine x with one of the two sines in the numerator. And now I have sine x on the, over cosine x on the left, and sine x over cosine x on the right. And that's why I chose not to make a substitution of tangent, although I could have.